Good morning, everyone. Today I will present a package classification algorithm called CODE-TSS. The full title of the paper is Tuple Space Assistant Package Classification with a huge platform on both search and update. This work addresses on the many challenges in package classification, achieving both fast lookup performance and fast royal update. In this presentation, I will explain the motivation behind it called TSS. It is architecture, the FICATS algorithm, the ESTSS assisted approach, and the experiment result. Package classification is fundamental operation in modern network. It is usual for firewall software switching, SDN controllers, and traffic management system. Existing package classification methods usually focus on either fast searching or fast update. Decision tree project provide excellent lookup speed but often suffer from expensive update and memory overhead. On the other hand, table-space searching techniques support efficient update but usually have slower search performance. The main goal of this paper is combine the strengths of both approach while minimizing minimizing their weakness. This motivation led, led to the development of TSS. The paper reviewed two major categories: a packet classification algorithm. The first, the first category is decision tree based methods such as headcast, highcast, hypercast, and hypersplit. Their algorithm Their algorithms are known for their fast classification performance. However, they often replicate rules across two major categories of packet classification algorithms. The first category, decision tree-based methods such as highcuts, hypercuts, and hypersplits. These algorithms known of the fast classification performance. However, they often replicate rules across multiple nodes, which increases memory usage and update costs. The second category is table searches methods. Their methods perform efficient update and binary memory consumption. However, the looking performance is generally slower. The author recognizes the trade-off and designed CutTSS and Hyper solution. Structure of CAD-TSS consists of two main stages. The first stage is called pre-cutting. In this stage, the rule set, partition and organize using position tree technique. The second stage, called post-TSS. This stage manages the different terminal nodes that remain after the cutting process. PSTSS is the input to this node. Together, these two stages create classification structure that support both efficient extraction and efficient updating. This architecture is the foundation of the entire algorithm. One important observation made by the author is the most real-world role contains at least one small field. Examples include long IP prefix and narrow port ranges. Based on the observations, the algorithm divides the rule set into multiple subsets. Each subset group rules with similar characteristics. This partition process reduces role overlap and simplifies the classification problem. It also decreases replication and improves memory efficiency. The partition stage prepares the data for the FICATS algorithm. FICATS, the main peer-cutting mechanism introduced the paper. Unlike traditional design tree algorithm, FICAT using fixed dimensions and fixed number of cuts. This design element they need to complex heuristics. The algorithm requires partition the search space and generate decision tree nodes. Some nodes become lost life nodes well, with their remaining terminal nodes containing many roles. Their different nodes are passed to the next stage for further processing. Picard provides smart and efficient way they route the search space. After Fi completes the work, some terminal nodes may still connection large number of roles. For this, nodes PSTSS is applied. PSTSS roles table spacing and perform efficient searches with the small spaces. They approach avoid excessive role repletion. They also support fast instruction and deleting of flows as rules they find classification structure achieved. Low memories, consummations, and efficiency update the stage transform the design trees into TSS assist design tree. This slide explains how classification and update performed. During packet lookup, a packet and enter the distribution and follow a path toward terminal node. If necessary, ESTSS is used search and remaining subset. Finally, the highest priority uh, matching rule is selected. For rule update, the algorithm notifies the responsive subset and terminal node. The rule is the instructed error or deleted, and only the affected ESTSS structure is updated, because only a small portion of the classifier changes. Update performances is significantly improved. The experiment results show that CAT-TSS successfully combines fast classification with the fast update, compared with traditional tuple space search methods. CAT-TSS achieved much better lookup performance compared with decisions tree methods, provide more efficient update and a lower memory overhead. The paper demonstrates that the hybrid architecture is both practical and scalable. In conclusion, CAT-TSS has an efficient package classification algorithm. They combine the advantages of decision trees and tuple space search. They offer they offer fast lookup speed, efficient update, and lower memory construction, making it stable for more network environment.